Okay, cool. So last class, we looked at binary tree, and more importantly, we were looking at what a binary tree is. Let's say there is a tree like this, 6, 7, and we were talking about the three ways of traversing a tree: pre-order, in-order, post-order, and we discussed that we were talking about why this is done, and that was this choice between, do you want to use a quick RAM, which is small in size, or do you want to use a hard disk, right? So we realize, okay, this is a devil we know, so we need to live with both the disk and the RAM, so it is what it is. Okay, so now one other thing with binary tree, the typical questions are, okay, so before that, binary search tree, it's like a binary tree, but the only difference is it is more ordered as per the size. So it will be more like the ones to the left are more younger than the root or lesser than the root. The ones to the right are, okay, so you cannot have anything high can be here. Okay, then we have to balance this, right? Okay, anyway, so that's how the whole idea is that this binary tree, the binary search tree will have these numbers, which on your right will be greater than you, the root, and the left will be less than root. Clearly, I'm not drawing a good picture of a binary search tree. Uh, okay, cool. So looking at my notes, oh, that's very okay. So just wanted to mention these two. Now, the reason I'm saying all this is, so this problems in binary tree. So 90% of the problems can be solved using a simple recursion like we saw last time. So the 10% is where we will see something known as level order traversal. Okay, so here we will see a level order traversal later. To start with, I'm going to just do some basic problems in a binary tree. So let me draw a Sainer binary tree. Okay, no, this is binary tree. This one is good enough, right? Okay, binary search tree. Let me see if I have drawn something in my notes. Okay, binary search tree. Just going to draw a good one, which I have in my notes. So binary search tree is 5, 3, 10, 1, 4, 8, 20, and 9. Okay, so that's a binary search tree. Anyway, let's start with the question today. So given a binary tree, doesn't have to be a search tree, given a binary tree, let's count the total number of nodes in it. How will you do it?
We can use any of the traversals we learned in last class. So whenever we were like printing the value, at that time we will increment the count.
Okay,
Because
so
we were printing the value at a node.
okay, so in that case, let me also write our thought process. The first one is paraphrasing, which is given a binary tree, count the number of nodes. So you think it through and say, okay, maybe there will be some leaves. We go back and look at the binary tree. We created here 3, 4. Okay, this is null. Here is null. The leaves will be null here. We'll have the next element null. Okay, so now you are saying we can kind of reuse the, okay, let's go back to the coding logic. Then there is, okay, coding logic will come back. Then we want dry run. edge cases, online code editor, and something else which I can't remember now. Coding logic, especially in recursion, what did we start with?
By me, myself.
What?
No.
No. Starting with function signature, and then the other one is me, myself. That's okay. Myself, and then we do a null/exit, and we do a parting gift. So if we were talking about one of the orders last day, if I can have, let's slowly start doing Python and see what happens. Def, what
No,
is
I
that
think
level?
I know how to do it in recursion, but not for traversal.
You mean you don't know how to do a level order traversal?
No, I don't know how to solve this question using the traversals, but I think I know how to do this using recursion.
You mean this binary tree count question using recursion?
Yeah.
Okay, so which is why I'm following what you just said. Okay, so I'm gonna call it count. And your point was we have a root R coming in. And last time what we did was, if this was, for example, so again, let's do a random binary tree, 3, 4, 7, 9. So if we wrote the function signature, and the next one is me, myself, where I am in 4, and I'm going to ask, okay, so if somebody tells me all, so your point was initially, let's try using the pre-order kind of thing we wrote last time, right? And modify that as a count. Okay, which is why I was saying, let's write a pre-order first, and I'm giving you the root R. And what we did last time was somebody told us, okay, I am here, the root node, and somebody tells me, what will you do? Somebody tells me your things before is done. So r.data, and in pre-order, we decided your left will come first. Is it right? Left will come first, then the center, and then the right. I think so. I
No,
always get
pre-order is NLR, node right left.
node light. Yeah, I just cannot remember this. So then it's right. So NLR. So now you will do same function pre-order of r dot left and pre-order of r dot right. Okay. Now, how did you say we can modify this? Okay, X condition if r equals to null, so return nothing. Okay, and how did you say we can modify this as a count?
I just thought that instead of printing r.data, we just count, increment the count. Like basically in this, firstly, we will have another argument to this method called count. Actually, I'm not sure.
Okay, so let's start with your first thought process. But feel free to say dumb things and stupid things, okay? Because it's a learning process for all of us. As you know, I don't sit here and judge. I am also trying to learn this. So if your thought was right, if instead of printing, can we do a count here? So which is, let's say, instead of printing, you're basically saying add a +1, right? Because you are added. And you're right. So basically all we need to do is here, when you're sitting in 4, somebody tells you, hey, here is a number of left children, here is a number of right children. What will you do? Your job is
to add yourself. Oh, sorry,
yes.
to call on the left and right.
No, it's okay. You're right. Remember, calling on the left-hand side is this guy, parting gift. Now we are still at the me, myself stage of this particular question, which is count, right? So let's even start writing a new function itself called def count of root. And so if somebody tells you your left child number, right? If somebody tells you have 4 children on the left, and somebody tells you have a 5 children on your right, so right children number, what will you do? You said
+1.
+1, perfect. And that is, you're done here. So now what is the exit condition? Same thing. Is it same thing?
Mm, no, it will not be same.
Okay, what do you want to check for at exit condition? So we did this, we did this.
What I'm thinking is, how will the function know that it has traversed all the nodes and now it is the time to stop?
Yeah. How did we do that in pre-order? The same problem, right? We traverse all this and we reach, when did we stop?
We checked with the node is none.
Correct. So why
Okay.
not that?
Yeah, it will be same.
Okay. So let's see, R is equal to none. Actually, I learned today that it is none in Python the hard way. If R is equal to none, what do you want to return?
Return 0.
Perfect. Okay. Return 0. So remember, if we were writing in Java, we would have thought of this return 0 while we wrote the function signature itself, because that forces us to write. Okay, so now we are done with the null and the exit condition. What was the parting gift?
Mm.
So this
Basically,
value you calculated, right? So let's call it counter or C, right? So this value C. Okay, so what do you want to do with the value?
we will call the return C.
Perfect. Return C. Okay, now what is the parting gift?
To me to call on right and left child to get the RCN and LCN values.
Perfect. So all we do is we copy paste the name of the same function. Count this plus count this again. All we do is r dot left, r dot right, and +1, and ta-da, we are done, right? So which is why I'm saying never ever think about recursion. You just have to follow these 4 steps and you will naturally reach there. In fact, today onwards, I'm even thinking we are ready to move on to the hands-on part. So what I will do is I will share my screen and we will do the same problem in LeetCode. Where is this now? Okay. I had to put it here. Okay, let's Google this. LeetCode, count nodes, binary. Perfect. So here's the problem, count complete tree nodes. So here they say, given the root of a complete binary tree, return the number of nodes in the tree. According to Wikipedia, every level except possibly the last is completely filled in a completely binary tree, and all the nodes in the last level are as far as possible. It can have between 1 to 2 power h nodes. Okay. So let's copy whatever we did just now. Do you remember what we wrote there? Are you seeing my screen with
Yes.
LeetCode on it?
Yes, I see it. Yeah, I was actually opening it parallelly on my computer too. So I think in this case we need a helper function because the original signature we cannot modify, and in our method we have count as a argument. So we will create another method like count nodes helper, and we will pass the root and initial count as 0.
Hold on. You said the code we wrote today. Oh my God. Please work.
Oh, I just meant that in our method we have a count argument, right? And
No,
in LeetCode, oh, we didn't have.
no, that's what I'm trying to show you. There you go. So remember, in your method initially, when you said count, we were having the value count. So that's the
I
beauty
see.
of
Sorry.
that's the beauty of this guy, right? Beauty of recursion. You don't have to worry about
Right.
passing anything because internally it's taken care for you.
Okay, yes. Got it. So,
So and if you're thinking of modifying the function signature, then you shouldn't be using recursion. You should be either using iterative solutions. You should be thinking differently. Like nobody asked you to use recursion in this case, right? But all I'm
Right.
saying is recursion is pretty much the solution of choice in count tree or anything binary tree, simply because it's like 2 lines of code if you can get it right, 3 lines of code, right? So yeah, so we wrote the function signature and we wanted to return LCN plus left children count, right children count plus 1. And we are going to check if our, okay, root equals none, we return 0. And then we come back to the parting gift, which is count nodes of, count nodes of root.left and count nodes of root.right. And I found today that these idiots like the cells to be explicit. The class is well written. And I think that's it. Let's see.
Return, yeah. Oh, the semicolon, the mixing of Java.
I know. All right, cool.
How did it work? You have semicolon there, right?
Yeah, same line, it's okay, no? Oh, semicolon, no, okay, no. Semicolon is okay. Python is very forgiving that way, which is why I don't like it, but it is what it is.
Okay.
Cool. So let me open up, maybe I'll do the same thing here. So that way I don't have to keep switching. And I'll continue writing in my iPad itself. Eventually you can show up. If I draw a line, it shows up a minute later. Cool. Second later, that's good. All right. So then the next question is, given a binary tree, find binary tree of positive integers. Actually, I'm just going to call it integers, positive or negative. Find if a given number x exists in the binary tree. Okay, so first step is write the function signature. Usually it's written for you from them. Oh, sorry. Actually realize I had to scroll down. Okay, what will be the function signature?
We will have a root node as an argument, and we will return true or false.
Perfect. So if you were writing this in Java, we would be writing public static Boolean. What is this? Find of root node. So that will be node of R. And you have to what else do you want to go here?
Oh, the value X.
Perfect, int X. Okay. So all I'm saying is you don't have to write your final code in Java, but this just writing the first function like this made you think about the Boolean value return. We can now start writing it in find itself, and we can say R, X. Okay, the value X. Okay, so we are done with the function signature. Step 2 is me, my. So let's go back to the picture here. Oh, I scroll, you scroll. Huh? Okay, let's try again in this case. It doesn't matter. 5, 4, 3, 9, 1, 2. Okay, so let's say you're trying to find the value X is equal to 9. And you are here. Okay, and somebody tells you anything below you is done, or so far everything, the job before and after you is done. What is your job?
To check uh, if I am X, like
Yeah, check if I am X, right? How do you do that?
if node dot val is equal to X.
R dot value equals to X. Then what will you do?
Return true.
Return
Otherwise,
true.
we call on the left and right child.
Perfect. Else, I mean, actually, in this case, Python, you don't even have to use else. That's fine. So we call on the left and right child. So let's call it left child and right child for now. Okay.
Mhm.
So somebody is calling the left and right child, but we'll come to it. And what is the exit condition?
If node is null, return
Correct.
false.
Null. Return false. I should invent a AI tool which takes my shitty handwriting and makes it look better. But it is what it is. Okay, so now let's come back
It's
to the
good.
part.
It's readable. It's good.
Hey, my cursive is better than this, at least but we'll see.
Mhm.
Anyway, now we come back to the parting gift. So what is the parting gift? The reason I'm saying is, okay, yeah, you tell me what is the parting gift.
Parting gift is
You said left and right child. What will you do with it?
I will call on the left and right child.
So you said find r
R
dot
dot
left.
left X
Okay.
and
What? Oh,
R
X.
dot
X. Yeah, you're
yeah
right.
X.
Okay. And do I do find r dot right?
Yes.
Okay.
And we can do something like if we find it on the, oh okay, nothing.
Okay, but this function is not returning anything yet.
Yeah, the default will be return false.
So you want the default to be return false.
Actually, can you scroll down because it's not visible?
Yeah, too many machines, too many machines.
Yes.
Okay, so return, you mean like return false here? Is that what you said?
Actually, we don't need it. Yeah, I'm sorry, I'm very confused. Yeah, we don't
That's
need
okay.
that
Okay.
return.
This is what I want to go through with you. I want you to think it through, right?
Yeah, I think this should be fine.
Okay.
No, we need to write return find. Return in front of find.
Return in front of find. Okay. And these two returns, there are three returns inside the else statement. Is that what you're saying?
No, we don't need that.
Okay. So let's go back to our, when in doubt, go back to Java, right? Public static Boolean find. And let's think always like it's almost like you are in the trees in the forest, but then you are become a bird and go up the forest. You go up the forest and you re-ask the question again. Okay, what is the question? They have given me in text, they've given me the root node, and I have to return if my root node exists or not, right? And in recursion, we did first step function signature, okay? Second step, we wrote my child. So me, my child. So my question there is, if you are here and somebody tells you left child and right child, what are they telling you? Last time they told you you have 4 left children, and last time they told you have 5 left children. Now
Okay,
what are they telling you?
they're telling that if X is found in either right child or left child.
Okay, so let's say they told you. So what will they be telling you? What will be the
True
value?
or false, basically.
Okay, so there's a true is your X is existing in the left is true and RC is false. Now what will you do?
Now I will basically perform an OR operation between the two and
Perfect.
if and return it.
Yes. So what we can do is we don't even need an else in else doesn't keep here. You are right. The only difference is this part was missing, no?
Yeah,
dot
this or part.
that's what I wanted you to naturally arrive at the thinking process through. And then, okay, we don't need this guys anymore. We don't need it. That's great. All right, so that's it, right? That's it. So if we had the parting, we had function signature, we had the parting gift, we did me, my, and we actually, here, this was our me, my, people told us who I am before me. And we then went to write the exit condition. And then we thought, okay, wait, if somebody else is telling me I have left children or not, what will I do with that value? We realized, oh, we had to take a OR of it. So let me also check if LeetCode has a find LeetCode find value in binary tree, maybe. Okay, binary tree search in binary search tree. Okay, you're given the root of a binary search tree and an integer val. Find the node in the binary search tree that the node value equals val and return the subtree rooted with that node. If such a node does not exist, return null. Okay, so in this case, it's different than ours because it returns the value equals val. Find the node in the BSD that the node's value equals val and return the subtree rooted within that node.
Oh, we have to return the subtree basically. Everything.
Okay, this will become just became complicated.
Yeah.
Or do you think you want to do it?
So if we find that node, instead of we return the node itself, right?
Okay.
Then if we return that node,
okay,
that
so
node is attached to its children. So
fair. Okay, so let's see.
let me also try
We
on
wrote
parallelly.
No, that's okay. It's okay. Let's do it together. Even I haven't done this before, so it's okay.
Okay.
So let's try. Our first step is function signature. That is done. Me and my. So let's say I am sitting in 4, where we are looking for 2, right? I'm sitting at 4, and somebody told me my left child is done, right child is done. So you check for yourself. So which is if root dot, what is it, data dot val equals to val. Return what?
Return root.
Perfect. This is return root. And so then we need to go check the exit condition.
If root is none.
Okay. Return what?
None.
Okay. Now we are done with we just need the last step. Last step is copying this guy, search BST of self.search BST of root dot left, comma val. Okay. What do we do next? Do we do an OR?
Yeah, I don't think we can do an OR. So we just call it again. Next line, we copy paste the same line on right.
Okay. Okay, so let's do this. This is the mistake we always make, which is we try to think on the fly, and our brain's RAM is a little confused. It doesn't have enough memory to keep. So this is probably not the best way to do it. So again, let's go back to public static node, find node, and we are given a node R. We are also given an int val. Okay. So now we just want to rewrite it in Python. We just do def find node of r comma val. Okay, that's a cleaner version. And this part we are right. So we did if r dot val equals to val, return r, and if r equals to none, return none. I doubt it's going to complain, but anyway, we'll see. So then my question is, what is next? You said, okay, we decided if we get from, you can always draw 5, 4, 3, 2, 1, and
Oh, actually, the question is a BST, not a
binary search
binary.
tree. Oh, okay, then we
Right.
probably don't need to do any of that.
I mean, we need to basically check if 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 X is less than the current value, we need to check in the left tree. If X is greater than the current value, we need to check in the right tree. So
Correct,
we will
correct. But
not
I'm
check
saying,
at both the directions.
yes, but I'm saying let's start with a binary
Mhm.
tree. It's the same logic, right? We started with recursion, then we started optimizing it and making it a binary search tree. So the only
Right.
advantage there is, so if it works for binary tree, it will work for binary search tree. Will it be the most optimal one? Definitely not. So I am trying to build at least get the foundation right.
Right. I think
Okay.
now it has become easier because we were thinking what to do with the two conditions, right? Or them or not. But now we will have like another if else, and we will return either of like we will have if value is greater than r dot value, then then return on the return call the same method on the left child, and else return on call the recursion on the right child.
Okay, you're not talking about binary search tree, right?
Right, right.
So I'm saying, why don't we do binary tree itself first and see if that helps? Because in theory, you could probably search through all the nodes and find the value, right? It's a very
Right.
brute force. I'm writing the right brute force first.
Okay, sure.
Okay, so all I'm trying to do is if I do find self dot find node r dot left comma val self dot find node r dot right comma val, and I don't know if I want to return anything yet. So what I'm going to do now is keep it there and let me do a dry run. Okay, so I'm starting with a dry
Mhm.
run here. I start with I'm at 5, so it comes in 5, and let's say we're looking for the value 2. So we are at 5, we're looking for the different color. 5, we're looking for the value 2. Is that color okay?
Yes.
Okay, cool. So 5, we're looking for the value 2. So we come here, is R none? No, it's not none. Then we do R is equal to val. No, we're not going in here. So when we do self.find node of R dot left, okay. So we go back here. This is 4, comma, same thing 2. Come back here, is none? No. R dot val is val. No, no. So we come back again 4. We're passing a none this time. None, null, whatever, null. And this value is 2 again. I'm not going to change 2 anymore. Null. Oh, this is none. Okay, so we got to return none. So now we were here and we return none. And we are
Mhm.
coming back and we are saying, okay, 4. Check my right side, didn't get any answer. I'm going to check, do I have a right value? No, I don't have a right value, so it's not going to go in there. So I'm back at 4. So nothing happened. We want the code to exit. Okay, the code exits, goes back to 5. Okay, and 5 says, okay, wait, I went to 4 because I was at my r dot left. I'm going to go r dot right, which is at 3. Okay, just going to go back here, 3. And that remains 2. Come back here. Is the node correct? No. So it says, let's go to the, we did this, here. Let's go to the left child, passing 2. Come back here. This is 2. Yes. Okay, it is returned, is not none. Yes. R dot value is yes. So we return R. Okay. So we returned R here. Okay, so we just found the right return node here. My question is, what do we do with that node?
So I'm thinking we can write if this is not the return is not none, then return it.
I see. Okay. Okay, let's both.
Return this if not if not something.
Yeah, 1 second. That's a good thought.
Otherwise, then move to the right.
Okay. So let me rewrite this. What you're saying is, and remember, one thing is it's okay to write long code. Don't try to
Mm-hmm.
complicate it in one single line. That will screw your brain up. You're saying
Okay.
if, sorry.
Can you scroll the page?
Yeah. Da, 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 da. This is good. This is good. This is good. Hope I got the right color back. No, it's a different color, right?
Yeah, it's okay, but it's better than the
Is it,
previous
is
one.
it now the same color?
Yeah. No, can you write something?
Yeah, equals to none, right? So I want if none, not none. If not,
Yeah. Then if
okay,
not,
so that
then
might
return R. No, yeah. Return R dot left, sorry.
left. Okay, so I'm even thinking why, okay, this is fine. So else we don't do anything. Is that what you
No,
wanted?
if else we call on the right. If this is none, then we check on the right.
But even that thing we need to check, right? If self.find node is,
Yeah, if this is also not none, then
okay, so why not do it
basically
this way?
else if we can use else if this is also not none, then return R dot left.
It will make it simple. I will do it. Tell me if this is wrong, okay? I might be wrong. Q is equal to this. So let's call it a different Q. Q is equal to this, and we go back saying if Q, if not Q equals to none, return Q, else, we don't want to, we'll do the same thing again, else, we'll do the same thing again, right? So why do we want this? We just do, when we go back, Q R is equal to, won't this work? I might be wrong, okay? Dot right, or val, same thing
Yeah,
if
it will work. It will work.
not Q equals to none, return Q. I mean, Python lets you reuse it, but I should be clean. Just gonna call it something else this time. QR. Yes,
R.
yes.
You can just call
R
it.
is already for root, right?
Right.
Okay. Do you
Can
think this will
you
work?
please scroll down also a little bit? Yeah.
Do
Yeah.
you think this will work for our basic things?
I
Okay.
think.
Okay, so let's do a dry run again. So we come back here. We were at the point
No,
where
we
we
have
were.
to actually return the node, right? So
We can return exactly what my child is giving to me, right?
right, exactly. Yeah. Okay.
So
Yeah, I think it
let's
should
let's
work.
do let's do a dry run again. Right. Let's go back and do the dry run this time. The one simple solution is put it all in the lead code and fight against the compiler. That will destroy your peace of mind. So, which is what my guru told me you should always do. When by the time you reach writing it on the thingy editor, you must be completely sure it's going to work. So we start at 5. We came with the value 5. Color. What color? I used to fail that game when we were kids, man. I couldn't understand why I always failed in that game.
Which game?
Color, what color? I miserably failed. I was like, okay, what's wrong with you? 5, 2, visible? Okay, visible. Cool. So we start with 5. 5 is none. Okay, if we don't go there, is 5 the value? No. Return R, node dot left is okay. We went to the node dot left. So we were here, we went here, 4. What is the 4's value? We come in 4. We tried 2, the 2 is not going to change. I'm going to keep it there. Is it none? No. Is it val? No. So find 4 are left. So we're going to send back null again and null. So come back null. Is it null? Yes, it is null. So we're going to return none. Is if find is not equal to none. Okay, now we come here. If q is, we got the value of this guy. Oh, sorry, I just realized that that line is still staying there. Okay, so we go back to the pen and we say, okay, if q is not equal to none, no, it is not, it is none. So we're going back to self dot find r dot right. So we are, wait, whose right was it? Okay, yeah, we're gonna come back from the right. Both of them are coming back null. And my only question is, when that happens, how will you return yourself? Maybe we just exit. Okay, we just exit. We go back to 5 and we go to 5's. At 5, we realize, okay, 5, this came out as when the answer to q is none. So is q is equal to none? Yes, it is none, so it's not going to go in there. 5 is right side. Let's say we are searching for 3 for the sake of simplicity. So we take 3 and changing the val's value to be 3, 3, and we go in with the value of 3. We come here, is it none? No. Is it value? Yes, yes. Okay, so now return R. So you return 3. And your S value is now the node which has the value 3. If not, S is equal to none, return 3. Okay, and our value is correct. Do you think this will work?
Yes.
Okay, let's try. In the name of the Father, and the Son, and the Holy Spirit. What are we count? No, how did we get there? Search in a binary tree. Okay. This one, okay, so what root none, return none, while return root. Okay, so we'll just follow q is equal to search binary tree as left. If q equals, okay, we want q not q is equal to none, we return return q. Return q. Self dot. Oof, it's a little bit tricky. It'll be interesting if it just works. Go dot right. If not s equals none, return s. Okay, let's read out loud. Def search binary tree. We are looking for the value 3, or in this case 2. We come with, okay, root dot none. 4 comes in. None root dot val is equal to val. Return root. Else we come back here. Q is equal to search self dot right left tree goes to 2. If not, q is equal to none, so goes to 2, comes back here, returns the value 2. If it is not none, it, yeah, so it'll go to return q, and we should exit, I think. I'm suspecting there might be an else somewhere, because, and in, anyway, let's run. Come this far, might as well.
Yeah. Yep.
Oh, fuck, it worked. Shit. All right, this is cool. Clearly, like I said, this is a terrible runtime because we assumed it's
Yep.
a binary tree.
Exactly.
Okay, so we have 2 more minutes. Do you want to modify it as binary search tree?
Yes, we can check if in line number 20, we can check actually before 20, before 19. So we only look on the left tree if the val is less than root dot val.
Calista, no, wait, let me finish this. And we do the same thing again?
Right. Else in line number 23.
But hold on,
else.
root dot val is yes, okay. And then we do the same thing, but root dot higher, right?
Yeah, we
Else,
just
you want an else, so we'll do an else also.
else.
No, wait. Nothing happening, Calista, wait. And this is how I don't get to do any social things after 5 o'clock. It is 5 and that na jaye. Chalo, chalo, mera time. No, wait. Dot right.
No, I think else is fine, right? We don't need, yeah. We don't need it.
Matlab,
We don't
we
need
have to
line
look.
number 24.
No, I'm saying, don't you want to do this?
No, because if it is less than, then In the
Actually, you
else
don't
part, it
need
will
to.
only come if it is greater than.
Very true. So let's see, it doesn't like the right tabs. We do this. And same thing if not is equal to none.
And like just want to mention s is equal to none. We don't need to check. If we just write if not s, it's same as doing
Oh, in
equal
Python,
to.
Python does that, right? If not,
Yes,
it
yes.
does that automatically.
Yeah, we don't even need the braces, but yeah, that's like,
This one?
yeah, this is good.
No, okay, no, root we need to check if
No,
it's
no,
none.
no, no. If
If
yeah,
not root, that's with this way, yeah?
yes.
Oh, I see what you mean. If not root, if not s. Yeah, this is, I learned Python or by myself, so I thought it's just an extension of Java. Big mistake. If
Actually, in
not,
the first one, we didn't have to write not because if root is none, then we want to return none, right? So if root. Oh, sorry. Oh God.
we want to return
Yeah,
if it's empty. So which is why I
yeah,
kind of write it all explicitly so that during interview, I don't even want to think about all that because I know the other thing. What,
yeah. I
so
agree.
that,
I agree.
okay, so this should give us a better value, I think. Let's read. If not root, return none. Screw this one. I can't even read this. I'm just gonna
I know.
safe. Better safe than sorry. If root dot val is equal to val,
Exactly.
return root, val less than root dot val, q is equal to sorry, I'm gonna go back to this. I cannot even read out loud. If q is equal to none, q not equal to none. Q is equal to not, q is equal to none. If not, s equal to none. Okay, return s. Else s dot self dot search, root dot right, root dot left. Q is equal to none. Okay, so we go basically looking only if. Why don't we do an else here also?
Right, right. Yeah, we can do. But we are returning from line number 17, right? Yeah, we can do it.
The reason is one thing will be less, right? One less calculation because if root is not equal to val, it can immediately go to the next else instead of checking this guy. Maybe. Does the function itself have a return? Doesn't matter. Okay, we'll see.
Interview.
Come on. Ooh, 41 millisecond. Not bad. All right. You're making some progress in life.